Alrighty, so here we have the last of our three theorems, the mean value theorem. So you can take a second to read it, and maybe, hopefully, now that this is the third lesson, these rigorous sort of math theorem statements are getting easier to interpret. So try really hard to figure out if you can figure out what this theorem is saying about a function. So we'll see f has to be continuous, so we'll notice the pattern here. Like all three of these theorems only apply when our function is continuous. In this case, we're also talking about a derivative, so we also have to say that the function is differentiable, so the derivative exists. Don't worry too much about the open interval versus closed interval thing. It's not going to make a difference in any of our work today. Then there exists at least one point C in A and B such that f prime of C equals this mess here. And this mess here is the average rate of change, right? So we've seen this before. This is the formula for the slope of our secant line. So, and that makes sense, right? Because it's called the mean value theorem. So what this is saying is that the derivative has to be equal to the mean value, or the average rate of change of a function at least once. Okay, I'm going to write that in words. This is pretty profound. Okay, so here's our formulation now in words. The derivative of a function must equal the average rate of change over an interval at least once inside that interval. Okay, so what this means, you guys have all seen, or at least are aware of the existence of, an application of this in real life. This means when you drive past a speed camera, so the way speed cameras work is there's two cameras along the road, right? So if you're driving along a road here, there might be a camera here and a camera here, and the first camera, if you're going this way, takes your picture, and then they measure the time it takes to get to the second camera. So if they use that to calculate the average speed over this stretch of road, and if your average speed is bigger than the speed limit, that means by the mean value theorem that you've gone over the speed limit at least one instant somewhere between the two cameras. Okay? So mean value theorem makes it easier to get speeding tickets, at least here in Chicago. And they actually added a bunch of speed cameras recently and made the requirements more strict, like made it easier to get a ticket. So pretty relevant here. Let's look at some problems. The delta math problems for this one are mostly pretty easy. So we'll start with these table examples, right? So we can take a second to read this one. So there exists a value c in the open interval 1 to 4 such that f prime of c equals negative 11 over 3. And you're like, where does this number come from? If I did the average rate of change, I would get negative 11 over 3. So it's saying the derivative is equal to the average rate of change. Now, on first glance, this one sounds pretty good, right? So we have the average rate of change equal to the derivative, and it says the function is continuous. However, this particular theorem has two conditions. So continuous and also differentiable. Okay, so it needs to say that the function is continuous and differentiable in order for the mean value theorem to apply. So here, our theorem does not apply. So this is a not necessarily true. So we don't know. Okay, so again, we're checking that both of our hypotheses are satisfied before we use the theorem. So we'll look at a couple more. So here's an example where the mean value theorem does apply. So it says that f is continuous on the interval and also differentiable on the interval. So continuous, differentiable, that means the MET does apply, which is good. And then we're just going to double check that we're talking about the average rate of change here. So the average rate of change would be negative 5 minus negative 1. And then 5 minus 3. Okay, so what do we get here? So notice, interesting. So notice what we get here. We get negative 4 over 2, which is negative 2. So these are not the same. So the mean value theorem applies, but the average rate of change over the whole interval is not equal to this derivative. So you might be thinking false. But if we look a little closer, we look at these points. Here we get negative 4 over 1, which now is the same as our derivative. Okay, so you may be thinking now, Mr. Wright, that's not the same interval that they said, which is a great point. But notice the interval 3, 4, well, that's inside 3, 5, right? So, like, if the mean value theorem applies to this interval, we can say that this value also exists in this interval, right? So any interval within the graph, if the interval, or within the function table, any interval within that table will satisfy this mean value theorem. So here we would say true. Okay. So pay attention to that. That is a likely source of error for you guys, I think. Any interval in the table can work. So you should look for the average rate of change between 2 points in the table, not necessarily just the first and the last point. And here we have this last case. So it gives us, let's take a look at what it gives us. It gives us the function is differentiable and that there exists a value c in the interval such that f prime of c equals 3. And 3 is the average rate of change. Let's see. So we get negative 10 minus negative 1. And then 2 minus negative 1. Right? No, other way around. Negative 1 minus 2. Which gives us positive 3. So that's our average rate of change over the whole interval. So this seems to be nice, it lines up, right? However, just because this derivative exists, it does not apply that the function is continuous, right? So this only works one way, just like we saw in the last lesson. So this works this way, but not the other way around. So on this example, when it's asking you to prove one of the hypotheses, we say not necessarily true.